welcome back. Happy Wednesday, it looks like. As a quick administrative announcement, I've moved back the due date for assignment 5 to midnight on March 17th, which is the last day that I can accept the assignment and still get your grades in on time. So it gives you a couple extra days. Before we get into the main material for today, does anyone want to bring anything up for discussion about the material so far, or assignment 5, or anything else?
I just have one question about assignment 5. Because it is due on the 17th, does that make it, like, is it going to be our last assignment, or are you going to assign anything else?
No, that'll definitely be the last assignment. So that's, yeah, by last day, I can accept stuff to get your grades in. That's like, grades are due right after that. So I'm not going to give you like a 0-minute assignment to do or anything like that. Yeah, this will be, so you'll have 5 assignments total for this class this term. And then, like I said at the beginning, grad students will be able to drop 1 assignment, and undergrads can drop 2 assignments. I don't know if there are any other undergrads in attendance today, so y'all get to drop 1 assignment. So if you're happy with your grades, oh, you're an undergrad, Stephen? Okay. So if you, so if you're happy with your grades on your first 4 assignments, then you can just not do the 5th assignment and or the, etc. But it is there if you want to do it. Any other questions? Okay. Well, so I'll continue on then. So today I want to continue talking about building models. So on Monday, I'd asked you to come in today with some ideas about what sorts of things you might want to model, perhaps from your own research, or even just like stuff you're interested in. I thought we could take some time, we could start by taking some time to like discuss some of those ideas as a class. So I thought we could do kind of a pitch session where you try to make your idea sound interesting so that other people might want to join onto your idea. And then also as part of this discussion, I'm hoping we can also talk about some specifics of how we might model different phenomena. So for example, if you say you're interested in like modeling how some sort of, just to pick a totally arbitrary example, pandemic causing virus spreads in humans, like maybe we'd want to think about how we're modeling people, or how we might want to model how and when the virus spreads and that sort of thing. And then like we'd also want to think about what the parameters of the model were. So like maybe starting infection rates or transition rates or circumstances under which transition could occur, probability of showing symptoms, test frequency or sensitivity, and so on. So maybe that gives you kind of a sense of what like things to consider when you're modeling stuff. And then we should also think about how we might actually want to like get at or estimate those parameters. So like maybe we'd want to fit our model using the Dartmouth COVID dashboard or CDC test data or something like that. There's also kind of an art to turning ideas into models. So I also think it's worth separating out the process of thinking about what to model from how we could model it. So maybe you only have ideas about one or the other, and that's totally fine and totally worth sharing. And then since it's often easier to come up with ideas about what to study or model than how to model it, I also want to share an additional way of thinking about the exercise of modeling and like framing what models can and can't tell you about like how the universe works. So there's this great George Box quote that says, "All models are wrong, but some are useful." And what he means there is that no matter how careful or detail-oriented our model might be, by definition of the journey we embark on when we make a model in the first place, we necessarily leave out some key properties of reality or make untested or even knowingly inaccurate assumptions. So if a model is like a simplified version of some real thing, that's easier to study by virtue of having been simpler than the real thing, then that simplification is also going to have a cost. So our model, however good we are at modeling, et cetera, is not going to perfectly reflect reality. And that's the all models are wrong part of the quote. And it's just something we like accept when we decide to build a model in the first place. And then the second part of the quote says, like, some models are useful. And that gives us a way out of models not being perfect by saying that like imperfection and imprecision and inaccuracies are all potentially okay. And so the trick is to make sure that the imperfect thing that we're left with can still give us some useful information or insights into the thing we want to know. So it's kind of analogous to like how the summary of a book or a movie might not capture all the details of the story. But if it convinces people to read the full thing, or if it gives people like enough of a sense of what happened that they don't need to read the whole thing, then or see the whole thing, then like the approximate version can still be of use. And then the other basic principle that's worth letting like percolate through your brain is that a model is kind of like a made up recipe that describes how some process happened or how some sort of measurement was made. And then like, since all models simplify reality, we already know that going in that the recipe is not going to be accurate and it's not going to capture all the details of reality. But that's not what we're trying to do. What the game is to ask, given the things we can directly observe, like maybe through the measurements we have made or can make, then if we make the simplifying assumption that the world works in exactly the way described by the model, then what could or couldn't we explain about those measurements? And then like what would the parameter of the model have to be, or the parameters of the model have to be in order to explain those measurements as well as possible? Again, assuming the world works in the way that's assumed by the model. So is everyone with me so far? Okay. Okay. So with all that in mind, let's do some brainstorming about like what to model or how to model different stuff. So does anyone want to like share or pitch an idea? Don't all talk at once.
I don't know how feasible this is, but something that I've been trying to wrap my head around is we have some. Also, I don't know if this. I'll just go for it. What a task we just ran. We had 25 listeners listen to 9 different stories, and it was between subjects, so 25 different listeners for each of the stories. And they had a sliding scale to rate their engagement throughout the course of these stories. And so they just would like go up and down. When they got more engaged, they would push the scale up, and when they got less, they would push it down. And it collected data on 1 second resolution through 15-minute stories. And I also have a data set of these stories collected from an RA who did some great work where he coded every time an object, location, or character was mentioned, and then coded each of those object, locations, and characters with unique names and things like that. So I'm interested to see if like there's some relationship between when these sort of like building blocks of the stories fall down and engagement. So if you see like all of a sudden like aliens are mentioned or something like that, if there's a spike in engagement, and maybe you can model these like patterns of engagement based on when these building blocks fall into place throughout the course of the story. But I don't know if that's too much to do now. That's just where my head is in the modeling world.
Well, it sounds super cool to me. It makes me think of a module we haven't gotten to yet, which is on natural language processing models. I think that's how I might approach this problem, you know, based on like my research and experience. So you could imagine like a model of the conceptual content of the stories. Maybe that's informed by those annotations about objects and locations and characters. And so you could kind of tweak the model to do a better job of explaining different aspects of the stories, like social aspects or tactile aspects or you know, spatial aspects, etc. That could be interesting to play around with. And then you could say, my model is that given, so you need some mechanism, like given that the story is about this at this moment, how does that affect your current or future engagement? And so the like modeling trick would be defining some process or function to turn the history of engagement and conceptual content until like up until this moment into a prediction about an engagement rating. So like the model would produce engagement ratings from those histories, or that would be one way to do this. And then, you know, that process might have parameters to it, and then what you're fitting would be, you know, what the actual stories were, and so you can fit models to that. You know what the annotations were, so that's like input to your model, and you know what the engagements were, and so maybe you'd hide all the, like, you know, you do some sort of sliding window thing where you hide all the behavioral ratings from a particular person up until the moment you're trying to predict. Then you have the model make that prediction. Then you like see how good your guess was. Then you slide your window forward by one and then make the next prediction, et cetera. And then like over time you could ask, you know, how good am I doing, and tweak the parameters to make the best estimates. Yeah.
Yeah, that'd be super cool.
Yeah, neat. Yeah, any other ideas in that space, or like, you know, other interesting questions you could ask, or thoughts or questions about how you might model different stuff? Anyone else want to share ideas?
It would be, oh, sorry, go ahead.
Would someone like to talk of the people who were trying to talk at once? You could all also just wait for each other to talk first and then kind of wait out the timer or something.
I can go first. This is also like me thinking out loud, but one of the things that I'm working on is asking people rate similarity between different emotional stimuli of different sensory modalities. Like it could be a video, it could be a story, it could be an audio clip, or it could be a facial expression. But what they have in common is they represent certain kind of emotion categories. So there would be a story that describes a character gets really angry about something. And at the same time, on the facial expression level, there would be someone making a face when they're angry. And then we will ask if how similar they judge this different stimuli from different modality, and see if there is any common variance that can be explained by emotion category, controlling, or even despite of the differences in sensory modality. And what I am struggling, or like struggling by, what I try to figure out is So basically we have 80 something stimuli, a list. And if you want to present it in a pairwise way, it's going to be 80 by 79. And then if you want to consider the ordered effect, it's going to be a lot more.
Sorry, you said my earphone cut out just as you said the noun in that sentence. Was it 80 stimuli or 80 participants?
80 stimuli.
80 stimuli. Okay. And then there's stories, facial expressions, and then did you say video or auditory or something? Or
Both of them, yeah.
okay. So is it like 20 of each or something like that? Or
so we can go a lot higher, but we just thought we already have a lot on our hand if you want to go with a pairwise comparison. So we try to find a way to sample some of the pairs and present or the subset of those pairs in a pairwise comparison fashion. But still, we want to find a way to drive the entire individual's similarity ratings with a subset, only with a subset rating, using something like collaborative filterings, things like that. It's just one of the ideal way that I've thought about.
And so does everyone rate all 80 stimuli, or everyone sees a subset?
A lot more than, it's going to be subset because it's going to be a lot more than 80, because 80 by 72 if you want to consider the order.
Oh, you're talking about recovering the pairwise similarities.
Pairwise similarity, yeah.
I see. And then so the behavioral data is like how similar on all these emotion dimensions was video 1 to story 17. And then so there's like, 600, or is it like 6,400 like possible things, and then one participant might make like 100 ratings, and then across all the participants you want to fill in that whole matrix. And then you want to know like, are two people similar, given that, and like the trick is they didn't necessarily fill in the same things. And then also like, is there some invariance, like modality invariant property of emotions that like comes through regardless of whether it's a story or expression or auditory clip or video?
Exactly. Yeah, that's the main question.
Very cool. Okay, yeah. So yeah, that's a neat set of questions too. Yeah, so I have some ideas. Does anyone, maybe instead of me like saying my ideas first, does anyone else want to jump in? Like, how would you approach this, or what do you think? Or Mijin, if you've thought of how to approach this, feel free to share your. So you mentioned collaborative filtering. I don't know if people know what collaborative filtering is, but that might be good to. I don't know. Does everyone know what collaborative filtering is? Does anyone not know? Okay. Do you want to explain, or?
You mean me, or?
Do you want to like say at a high level what collaborative filtering is, or does anyone want to explain?
So I haven't actually implemented it in any analysis, okay. But my high level understanding is, so it's one of the techniques they use in a recommendation system, like movie recommendation and music recommendation. So based on similarity between two items, if one person say, I really like this item, and they give a higher recommendation rating for the other item that's similar to that, or similarity rating high by someone who has similar taste or something. That's my high level understanding.
Yeah, I think that's so this was developed as part of like the Netflix challenge, which was a few years ago, like a decade ago, actually, now that I'm thinking about it. It is a few, but yeah. Yeah, and the idea is like, you've seen some movies, other people have seen other movies, other people's movies somewhat overlap with yours. And then what I want to know is like, which movie should I see next? And so like, if you've seen movies in set A and I've seen movies in set B and those sets aren't identical, then like if your tastes and my tastes in movies are similar, I want to pick like a movie you really liked from the set of movies you watched that I haven't seen yet. And so the trick is, first you want some way of saying like which movies are similar to each other. And then you want to measure of like which people are similar to each other. And then you can say, given given the movies I've seen, I want to do something like compute a weighted average of how much I'll like the movies I haven't seen yet, given where the weights are determined in part by how similar those other movies are to movies I have seen and liked, and also how similar I am. And then like those guesses are based on other people's ratings. And then how much I weight those other guesses are based on how similar the overlapping parts of my ratings are with their ratings. Does that make sense? So the way that could work here would be, maybe you have some way of saying how similar emotions are. So like, well, I guess we could imagine various ways of getting at that, but so I don't know, let's say there are 5 different possible emotions people could exhibit. I don't know the exact number. I don't know if anyone knows the exact number. Depends if you believe in like the emotional granularity literature, I guess. Well, let's say there are just 5. Then you could say like, how similar is happiness to sadness to anger to surprise, etc. So you got your ratings. And then you can also say, well, for each clip, I've rated a subset of the similarities. And so now I can say, so I guess we want to have a model of how similar the different clips are to each other, actually. So we'd have to somehow get that from the emotion similarities. So if you have some idea about the mix of emotions that each clip exhibits, we'd have to maybe go from emotion similarity to mix of emotion similarity. And that would give us the similarities between clips. And then the collaborative filtering approach could say, for the things I rated that were similar to the things that you rated, like, can I stitch together the missing pieces by doing this weighted averaging trick? Yeah, cool. So that would give you the full matrix for every person, or an estimate of the full matrix for every person. But then, yeah, and then, so that definitely seems useful. But then then we need a way to like answer your questions, like how similar are different people or different people's ratings of the same types of emotional stimuli across modalities. Yeah, so those are challenges. Does anyone have suggestions, or like, yeah, well, first of all, does anyone have suggestions? Maybe we'll start there. Like, suppose Emotion Corp, which is the world tech leader on emotion processing and understanding, is like, okay, like you seem smart. You're an expert in human psychology, coming from fancy college Dartmouth. I'm going to pay you, like, I have this budget. I have too much money to know what to do with. I want to pay you $1 billion to design a study to really answer these questions. But I'm just going to lock you in a room until you answer it. And then at the end, if you like give me a good answer, I'll give you the $1 billion. So like, yeah, like, I don't know. I guess you don't have to get your $1 billion. You might want it though. How would you approach it? Would you just give up and just run away? Or would you like start to guess? Might as well guess, right? It could be a bad guess. That's okay.
Wait, I'm sorry. What is the question exactly? Like, like what is it that we would need to answer?
Well, Eugene, do you want to restate your?
I think maybe it wasn't clear, but my research question with this design is whether there is anything determined by emotion categories, but invariant to sensory modality. So when people see something like sad in a video or hear something, hear a sad story, is there anything that we can capture in common between those two stimuli, even though this, in spite of their sensory differences? So one thing I think I would do if I get a better sense of how to get the similarity metrics or the whole like individual similarity metrics across the stimuli is like whether we can explain the individual differences between, like, someone might say this video is angry and someone might say this could be funny, and then we can, I mean, this is a subjective processes that we can't really observe, but by relative measurement like similarity, we might be able to explain why somewhat, maybe not why, but there is an individual differences in subjective experience of emotion with the same sensory stimulus. So that's the idea.
I don't know for sure. I know with prime, one way to get at shared representations is priming experiments, where, you know, if you show one stimulus and it shows representation, you'll be sort of faster, more accurate on the next trial. I don't know if that works for emotions. If, you know, you can prime with one emotion, then they should, if you show the same emotion, people are faster. But if that were the case, you could then do it cross-modally to see if there's a shared or at least a transfer of representation. So you prime somebody with something happy or funny auditory, and then you present them with something visual that's the same or different emotion. You can see if there are cross-modal priming effects. A behavioral way to get at shared representations. Though that really relies on there being priming effects for emotion. And I know priming effects for some things in the visual literature, but I don't know the literature well enough to know if that would work for emotion.
That also requires collecting more data, which yeah, that sounds like a cool experiment. And you can imagine also like modeling, well, maybe there's some, like what predicts reaction time, you could say like part of it is the modality and part of it is the emotional similarity between this stimulus and other things I've seen previously. And then maybe you want to do some kind of mixed effects model or something where you're trying to separate out or separately estimate those things. Yeah, but that would be a neat experiment. Yeah, definitely. I guess another thing that's missing here that's a challenge is like you have the similarity ratings, but what you're really trying to get at is like what are the emotional dimensions of each stimulus, or like that's in part what you're trying to get at. So it's like you have this extra hidden piece. So we call that like a latent variable in the modeling land. So it's like you think that what's driving similarity structure is the like emotion dimensions and emotional similarity, but you don't get to directly observe what those features are. Yeah. there's another like kind of geometry trick where if you have a similarity matrix between a bunch of pairs of measurements, you can use an approach called multidimensional scaling to recover feature vectors for the things that went into that similarity matrix. So you pick the number of dimensions, and then you can mathematically recover a set of feature vectors that could have generated that similarity matrix. So you pick the similarity metric and how many dimensions, and then out of multidimensional scaling, which is, we can think of like a black box. I mean, how it works is interesting, but we don't have to discuss that now. But then, you know, you could think, okay, well, if you jiggle around the coordinates in this space enough, then maybe you can come up with a configuration where like points that are similar in your similarity matrix are nearby in this space. And then points in the space correspond to feature vectors. And then you can treat those feature vectors like emotion dimensions that, I mean, you won't have the human labels for them, but
We
yeah.
will have the human ratings for that. So we are going to
Oh, you
get
will?
rating, yeah, for 13 different effective features, but we can do it per stimuli, per stimulus for that, because we can just construct.
Because there are only 80 of them. Yeah, there's
so
only,
you
oh,
can
that's
just do
cool.
our-
Yeah. Well, there you go. So yeah, so then you have data for that. So you don't need to do multidimensional scaling. Very cool.
But we can, the reason why we get the direct pairwise comparison rating along with that feature, the separate feature rating, is because we don't know what features actually play the strong role in that judgment. So we want to get the features that that use in the literature a lot, and then we can compare the actual pairwise similarity to that. And maybe the MDS is one of the things we are considering, and compare what MDA extract can be similar to any of the combination of those features.
I see. That, yeah, okay. That makes sense. So in that case, sorry, just knocked over my space heater there. Didn't cause a fire, so I'm happy. Okay. That makes me, okay, that's making me think of like, almost like a representational similarity analysis sort of approach, where you take like, you can ask, let me come up with a set of weightings over features. So you get your emotion ratings for each stimulus, and then maybe you'd want to define some extra feature dimensions based on modality. So maybe you have like, you know, a indicator vector to say whether it's a story or facial expression or auditory or video or you know, et cetera. Maybe those are all the modalities. And then you just append those 4 dimensions onto every feature vector. So you have like, let's say you have 5 emotion dimensions, and you get your emotion ratings for each stimulus. And then you add 4 additional dimensions. So each stimulus is like a 9-dimensional vector. And then what you want to know is, what's the weighting over those dimensions that explains the observed similarity judgments that people give. Yeah, so you'd want to, there are various ways to solve this. One approach is to use some sort of a mixture model where you have like mixing proportions of your weights, and you use those to determine how much to weight the similarity like along different dimensions. So you can imagine extremes would be like only weight the emotion parts and ignore the modality parts, or only weight the modality and ignore the emotion parts. Or like the interesting things would be somewhere, well, maybe those are interesting. And then, but probably neither is true strictly. And then, you know, maybe you want to know the mix between those that explains the actual data. And so you could construct a similarity matrix that you estimate based on just the emotions. And that would give you pairwise similarities between all your stimuli. And also, you could construct a predicted matrix just based on modality. And then what you want to fit would be like, what weighted combination of those similarity matrices explains each person's observed similarity matrix. So you could use like regression to recover those, or you could use a fancier model if you want, but regression is probably the easiest. Yeah, and then if you want to look at individual differences, you could say like, what is that, like, fit the model independently for every person? What is that what is the distribution of those mixing proportions? You really only need one mixing proportion. You could say like, if your mixing proportion is like X, you could say, and like X is between 0 and 1, you could say X times the emotion predicted matrix plus 1 minus X times the modality predicted matrix equals your observed matrix. And then you want to solve for X. So that's the thing you're solving. And then you could say, what's the distribution of X look like across people? And is it like, if it's unimodal, that might suggest maybe people are kind of all pretty much the same, but there's some variability. Or if it's like, got multiple peaks in that distribution, maybe there are different types of people that could be interesting to try to tease apart. Yeah. Cool. You could also imagine like a process model where like you want to explain, I've just seen something. So I'm like, pretend I'm the model's brain. Now I see something, and then as a function of the attributes of what I've just seen, I'm going to produce a similarity. And then what you're asking me about, I'm going to produce a similarity rating. And like, you could get fancy there and say, maybe I'm making judgments based on the history of things I've seen up until now. So like, if I see 10 different clips, maybe I'm using that as my reference to say how like the range of similarities between things, like it kind of sets the bound, like the anchor points of my scale, my mental scale. And so maybe that could be interesting too. Like I'm not going to judge based on the similarity. Like if I'm judging similarity of these emotion clips, I'm not going to judge like how similar is this movie clip to like a slime mold, because that's not in the space of things that I'm comparing to, or even like movies about slime molds that might be like similar in modality, but not content necessarily. Well, I'm just making assumptions here, but yeah. And then, yeah, so like that piece could be interesting too. What causes someone to make ratings, and what scale are they using? Is that stable over time? Man. Cool. Okay, any other, or yeah.
Yeah, I was just say, cool, thanks.
Yeah, sure. Cool, yeah. Anyone else want to share an idea, pitch an idea? You don't have to, yeah. Sarah, yeah.
Well, I don't know if it really fits or not. I mean, mine is for behavioral data with an experiment, and there's basically several different possibilities that could lead to the observed outcomes, and it would just be trying to see sort of what mixture of combination of those possible factors are explaining the behavioral data that we get.
Yeah,
I don't know
cool.
if that really fits those.
Yeah, that sounds neat. Yeah, do you want to tell us a little more about
Sure.
what the behavior is and what you're thinking in terms of?
So the experiment is pretty simple. We just show people faces at sort of one of 8 positions here.
And there are these half faces.
Different, but this is the idea. And they're half faces. And so it could be the left or right half, and then it's not always the right half in the right visual field. It could be the left half in the right visual field, and so on. So you could have any sort of combination. And the experiment, you've learned these phases beforehand. So you're fixating, and then I show you half of a face in one of the visual fields. Could be left or right half in either visual field. And then I just say, who was that? And you've learned 4 identities, and you say which of the 4 it was. So we basically have an experiment where our dependent variable is recognition accuracy. How accurate were you? And so there are a few things then that could explain the data we get here. The first is simply the distance that we showed something from fixation. This is sort of a little bit of a sanity check as well, because if I show something way off in your visual field, it's going to be a lot harder to recognize than if I show it right at the center of your visual field. So we'd expect this. And this is sort of idealized data that I'm showing here, where you just expect a drop off. And it should be applied equally to the left and right half of the face. And in both visual fields, there should be sort of equal drop off. The second theory, and this is something that's been observed in the face literature, is that there's a left visual field superiority. So if I show anything in the left visual field, you're just going to do better. Now, this is incredibly exaggerated data, so it does not actually look like this. But this gets the point across that if I show the left or right half of the face, the left visual field, you always do better. Now, this isn't independent from distance from fixation. As you can see here, I've sort of thrown in the distance from fixation into this model. So this is also a combination. I guess if I technically did this just as purely left visual field superiority, these would all be at 1. But this is sort of a combination of models 1 and 2 here. Since I sort of expect this to always be true, I couldn't imagine running this experiment and this not being a true, or at least an important factor. We could have same visual field superiority. So if I show the left half of the face, you do best when it's in the left visual field, and you do best with the right half of the face in the right visual field. And again, that's not even independent of the other 2 theories, because you could imagine that interacts with distance from fixation. It also interacts with left visual field superiority. So things can get really complicated there. Then it could be also, instead of distance from fixation, you have also distance from canonical position. So this is sort of a shifted version of distance from fixation, where instead of the left half of the face, its sort of center being at 0 degrees, its center is just to the left of fixation at, let's say, -1, because you tend to view the left half of the face when you're looking at it just to the left. If you're fixating the center, it tends to be just to the left of your visual field normally. That's kind of the, all of our built up visual experience. The left half of the face is almost to the left half. So you can imagine it's not actually distance from fixation that matters. It's how far is it from your canonical position. That is what matters. So that's another.
Just to make sure I understand that one, and like the distinction, but with the previous idea, whatever the word is, you're saying like you're thinking for that explanation, like canonical position, if it was a full face, where would you expect it to be? And then where would you say the position was if it was a full face? And so you're like position computed using the filled in face, is that?
Yeah, if we just think of our usual visual experience, we tend, unless someone's sort of standing kind of peeking behind a doorway or something, we tend to see people's full faces. And for example, I'm looking at your face right now as I talk to you, and I sort of fixate on it, and I'm simplifying a little. You tend to not fixate right in the center of the face, but assume on average that we do. The left half of your face, from my perspective, is going to be in my left visual field, and the right half of your face is going to be in my right visual field. And that's sort of our canonical visual experience, is that our eyes, because we tend to fixate on face. Again, that's actually simplification. We don't really do that, but is that, yeah. So you just tend to have this correlation. Left half of the face will always be in left visual field. right half of the face in the right visual field. And so it could just be that your brain gets wired up so that that becomes the center, that it's not truly the left half, its center is not actually 0 degrees, it's shifted a little bit. So this is basically a shifted version of that first theory. The drop-offs were a little different here, but yeah. So you can see it just looks like a shifted version of that original distance from fixation. And then we could have it be that one half of the face, we're just better with one half of the face. So if I just show you the left half of the face, regardless of visual field, you're just better at recognizing the left half of the face. And if I show you the right half of the face, you're worse at that. Or maybe you're better with the right half of the face. And now the tricky thing here is, I presented these individually, and for all these, I sort of thrown in the eccentricity effects because I expected all. But you could imagine these actually we could have multiple of these factors and they all have different weights. So I see a few challenges here. One is sort of with these different possibilities, that's a lot of possible interactions. That's also potential collinearity between all these models because it could just be hard to distinguish. For example, distance from canonical fixation, distance from fixation are likely to have some, collinearity between them, and it could be hard to tell apart these two hypotheses, or you might not necessarily have the resolution to do it. And so, yeah, I've just been trying to think through then how best to go about teasing apart these different factors, and any ways I might need to sort of simplify or specify this model in a way to work with. Understandably, I can't run people for 5 hours on a task with a million trials. I'm gonna have
sure, yeah. So there's a limit to how sensitive or like how much signal you're gonna be able to get, because like yeah, okay. Yeah, so there are a lot of interesting things here. One is that yeah, all three of these examples have been like different styles of models, which is interesting. So like, are you like explicitly modeling the content? Are you just assuming the content exists, etc.? This feels like you could imagine modeling face processing using like a specific model of how faces like enter your visual experience and propagate through your visual system and memory system and get recognized or judged. That would be interesting. But it seems like the level that you're asking is really more of like a kind of regression. Like you're kind of assuming that your brain does these things somehow, and then you want to know like what's the appropriate mix. And then there's this extra challenge that like potentially, well, you called it collinearity, but like it's another way of framing it would be like, so you have like model A or model A plus B. So model A plus B is more complicated, but also incorporates model A. So like from a strictly like how good does it fit the data standpoint, model A plus B is always going to beat model A, because at worst, you could just have the B weight, like if your data is exactly explained by model A plus some noise, the like A part of the model will explain the data, and then the B part will explain the noise, and then it'll always win. So there's this potential confound or trickiness between what's actually happening, and then also like these models or the potential models vary in their complexity and therefore flexibility. So one way, one thing to look into would be AIC and BIC. So a Kaike information criterion and then Bayesian information criterion. So these are both kind of similar conceptually, but the general idea is to, I think it's kind of what you're wanting to get at. It's like how well does the model fit the data, taking into account how complicated the model is. And that's going to allow you to directly compare these different approaches, factoring in like how many parameters each approach has. So I think the like BIC is more in style right now than AIC, but it used to be AIC was more in style. And so I don't know that one is truly strictly better, but probably easier to publish on BIC now. But yeah, but like you can imagine you know, what would the parameters of the model be? You could say like, well, you have some factor that's like distance from center, then another factor that's like left superiority or right superiority, and then like distance from canonical position or center of the screen, et cetera. Or well, I guess I already said that. Or like left versus right face side preference. So there's like left versus right visual field, left versus right face. So you have all these factors, and then what you want to know is like, so essentially you can explain all your models by forcing some of the weights of those factors to be 0. And then also you want to know like, if the influence of that factor is not 0, what's the right parameter to like control the slope of how my responses change as a function of distance or stimulus type. So you're kind of fitting both of those things. Yeah, I'm kind of imagining like a regression framework where you're just like, you know, you have to write down your equations for how recognition performance changes with, or labeling performance, whatever, you know, changes with left versus right and distance, I guess canonical, and degrees visual angle from fixation or whatever. And then you want to know like, what are the weights of these different things? And then your model comparison could be, I mean, you could either fit everything simultaneously, and then you just might find some weights are going to be near 0. But you might also find that the best prediction is just a combination of everything, because that's the most flexible model. And so you could like do a little better than that by forcing some of the weights to be 0, and then the number of parameters is fewer for those cases. And that's where like AIC and BIC can come in to fairly normalize for those things. So it's like, does the cost of adding this new parameter justify the benefit, the explanatory benefit I get from adding that parameter? Yeah, so that's a cool, cool modeling setup too. Okay.
Thanks for that.
Yeah, sure. Let's see. We probably have time to talk about one more idea if anyone wants to bring something up. Or I could just say a bit more about how to move forward from here. Okay. Well, cool. Yeah, so those are neat ideas. Yeah. Well, so what I think those ideas were really neat. So I'm happy that we got a chance to like talk through some of those. What I was imagining for this like exercise would be then breaking off into groups and maybe like opening up a collaboratory notebook and like actually jotting, like making some Python classes or coding some stuff. We don't, I think, have time for that in our last 5 minutes of class today. So I guess maybe I'll pose it to you. So like we have, I think our last day of class is in 1 week. So we have Friday, Monday, and Wednesday, and that's all we have left. The modules that you expressed an interest in learning about that are remaining are natural language processing and time series analysis. So maybe let's just vote on, like, do you want to try actually implementing some models, some of these models that you talked about, or like talking about how we might implement them, or do you want to cut this off and go on to probably the next logical step from here would be like natural language processing. I'm thinking. So we could move on to that on Friday and just have like, we're not going to be able to dig in depth into any of these, but I could, introduce you to some of those approaches and techniques and, maybe put some sort of demo together that you could play around with. Okay, so who would like to do another day of modeling where we like try to implement some of these models so you get some practice actually like making a model? 1, 2, okay. How about moving on to natural language processing? Okay, that's a majority. Okay, so we're gonna move on to natural language processing then. So yeah, that it feels like a somewhat unsatisfying, like I don't know, an unsatisfying like rush through building models. You could really teach a whole course on building models, and I have some pointers actually to full courses. Todd Garekis teaches a really amazing course, and all the materials are online and linked to in the our course outline. So if you want to get practice building models, that's I'd recommend taking a look at those materials as a place to start. But in general, the approaches are going to be similar to things you've already done in the class. Like maybe you want a Python class for representing like a mental state, or maybe you want to use scikit-learn or SciPy to do a regression analysis, that sort of thing. That's the name of the game. And then you'll also get some practice with this in assignment 5, where you like build essentially like a regression type model where you're fitting like an exponential decay curve to a data set to like explain learning, and then a more process oriented model where you're like trying to explain using more explicit model, like how do you actually build up a cognitive map of a new environment that you're navigating in. So those are two like super different approaches that are both useful, but like, differently informative. Okay, so yeah, so sorry we didn't get a chance to actually like implement these, but on Friday, we'll dive into natural language processing. So for Friday, why don't you take a look at stuff that looks interesting and or useful from, I think it's module 9, but let me double check that. Yes, module 9. And then maybe I'll put some sort of demo together where you can like play around with some, text data sets, and yeah, we'll talk about how to model them and work with text data. Cool. All right. Any questions or final comments before we wrap up? All right. Well, in that case, have a great rest of the day and see you all on Friday. Take care, everyone.